Light can illuminate, reflect, even cut through metal, but in this experiment, it does something stranger. It reflects off a mirror that isn't solid and launches electrons to near the speed of light. Not with magnets, not with miles of vacuum tubes, just a foil thinner than a human hair and a pulse of light shorter than a blink. In a simulation study published in June of 2025 titled High Charge Relativistic Electrons by Vacuum Laser Acceleration from Plasma Mirrors Using Flying Focus Pulses, researchers modeled a setup that behaves like a miniature particle accelerator, one that could fit on top of a table, yet rival machines the size of cities. The idea may seem futuristic, but the physics behind it, as you will see, is very real. And the possibility of this being reality is closer than we may think. Could the future of high energy physics fit in a single room? Now, most people never think about particle accelerators. I said most, but they have reshaped our understanding of reality. They've confirmed the Higgs boson. They probe the early universe. They have even helped design advanced cancer therapies. But there's a problem. They're massive, expensive, and rare. Take the Large Hadron Collider. It's over 17 miles long. That's long enough to go around an entire city. Here it spans two countries and it cost billions of dollars to build. That's the scale we've needed in the past to reach these energies. Until now. Luckily for us, some researchers asked, what if you don't need 17 miles? What if a plasma mirror and sculpted light pulses could do what once required miles of vacuum tubes? This study takes that question seriously and starts to answer it. And if it works, it could open up the door to something extraordinary. Particle accelerators shrunk to the size of a table, not just for national labs, but for hospitals, research centers, and maybe one day, small experimental teams. We'll return to that big picture later. But first, what exactly is a plasma mirror? A plasma mirror may sound like science fiction, but I promise you it is a very real piece of laser technology. Here's how it works. You start with a solid target, usually a thin foil. You hit it with a femtosecond laser pulse, focused to intensities exceeding 10 to the 18th watts per square centimeter. That pulse is strong enough to rip electrons from the atoms, vaporizing the surface into a dense cloud of plasma. In that moment, the front edge of the target becomes a dense electron layer, so reflective it acts like a perfect mirror for the next pulse of light. These plasma mirrors can reach electron densities of over 10 to the 23rd particles per cubic centimeter. That's dense enough to bounce back even the most intense lasers we can make. Only this mirror doesn't crack, doesn't melt, doesn't wear out. It reforms with each shot, lasting only as long as the pulse, then vanishing. And because it's made of plasma, it can survive laser intensities that would destroy any normal optic. That's why researchers use it. It's not just durable, it's the only kind of mirror that can handle what comes next. Because in this experiment, the reflection is not just bouncing away, it's been shaped on purpose to chase the very electrons it just helped set free. In any accelerator, whether miles or just millimeters, timing is everything. If electrons fall out of sync with the accelerating field, they slow down or scatter. That's the challenge with vacuum laser acceleration. A conventional laser pulse moves at the speed of light, too fast for electrons to keep up. The pulse races ahead before it can do much work. But what if the pulse could slow down just a little bit? What if we could make the peak of its intensity chase the electrons instead of leaving them behind? That's the idea behind flying focus. It's not a different laser, it's a different way to shape the pulse in time and space. By chirping the frequencies, stretching some, compressing others, and focusing them at different depths, the pulse's focal point begins to move, like a ripple down a fiber optic cable. And crucially, we can control that speed, even set it to a velocity just under the speed of light. In the simulation, the researchers use a 20 femtosecond pulse with a central wavelength of 800 nanometers, focused to just 5 microns in diameter and tuned the focal point to travel at 99.7% the speed of light. Now, instead of the electrons falling behind, they stay locked in the beam's sweet spot, gaining energy every step of the way. So, what happens when you combine the two? A plasma mirror that reflects intense light and a flying focus pulse that moves just under the speed of light. That's where the real interaction unfolds. Here's what the researchers did step by step. If you want to skip ahead, feel free to do so. But they began with a 500 nanometer thick foil. They hit it with an ultra short laser pulse, ionizing the surface and forming a dense plasma mirror. Then came the second pulse, shaped into a flying focus. As it reflected off the mirror, its moving focal point synchronized with the velocity of the newly freed electrons. That reflection was not passive, it was a handoff. The shaped pulse transferred energy with precision, grabbing those electrons and accelerating them across hundreds of microns in perfect phase. The simulation used a full 3D particle and cell model with a computational box measuring 80 by 40 by 40 microns, tracking both fields and particles in fine detail. Together, the beam produced was high in energy, high in charge, and impressively focused. Specifically, electrons reached peak energies of around 1.05 giga electron volts with over 12 nanocoulombs of charge in the high energy portion. The energy spread was around 10%, and the divergence stayed below 20 milliradians, tight enough for real world applications. And if that sounds small, consider this. Reaching that energy with a traditional accelerator can take hundreds of meters. Here, it happened in just under a centimeter. Just laser, plasma, and timing. This reminds me of the 1930s when the first cyclotron fit on a lab bench. It launched a revolution in high energy physics. Maybe history is about to repeat itself. Ultimately, this is not just about speed, it is about access. Compact accelerators like this could reshape how we apply high energy physics. Hospitals might one day be able to use them for targeted radiation therapies without the cost or scale of today's linear accelerators. Researchers could unlock new capabilities in ultra-fast imaging, capturing atomic scale events in real time. And maybe, down the line, this technology could support novel propulsion concepts where charged particles are pushed and steered by light itself. We're not there yet, but the foundation is forming. This study was a simulation, a full 3D model using real-world laser specs and plasma target parameters. To make it real, engineers will need to manage debris, prepare targets with high precision, and address issues like laser contrast and thermal damage. Still, the core concept is solid. A mirror made of plasma, a pulse shaped in time, electrons riding light and accelerating toward a new kind of physics, and maybe toward a new kind of access. We just explored a tabletop accelerator built from light, where a plasma mirror and a flying focus pulse work together to launch electrons to near light speed. It's compact, it's precise, and it's filled with potential. But where could all of this lead? What happens when particle acceleration becomes as accessible as microscopy? Could it unlock new forms of medicine or deeper ways of understanding the universe? And what else might we be able to shape with light that we once thought only matter could control? If this sparks something for you, let me know what stood out or where you still have questions. And if you come across any scientific paper or study that deserves more of a spotlight, drop it in the comments below. If you made it this far, I so appreciate your time. Be sure you are subscribed. Be sure to hit the like button and leave me a comment. Until next time, take care.